Excellent. This is your Thermodynamics 2 class. This is lecture number 17. There is only 15 students, 5 students right now. So can anyone text to all the students that join the lecture?
जी सर क्लास ग्रुप में मैसेज कर दिया.
Thank you. We will wait for 2 minutes and then we will start. Okay, so coming towards the lecture number 17. So before starting the lecture, okay, I have to just announce one thing that now you already know that the rest has already communicated to the faculty that we can start the quizzes, some online quizzes. Okay, so from the next class, in each class there will be one quiz. Okay, because we have to complete 9 quizzes for this semester. Okay, so tomorrow there will be one quiz related to dual cycle. So which we already covered in the previous lectures. Okay, so this is a simple one because for 15 minutes we have to revise this dual cycle topic, okay, for tomorrow's session. Okay. Today is again chapter number 9, gas power cycle. Okay, so in the previous classes we already talked about dual cycle, diesel cycle, Otto cycle, Stirling engines and Ericsson cycle. So these all type of engines which we already see in the previous lectures are basically the reciprocating engines, okay, where we have to convert the reciprocating motion into some useful sort of work. Okay, but there are some type of engines which convert the rotary motion rather than the reciprocatory motion. So these engines which use the rotary motion, these are called gas turbines. So gas turbines are another type of gas power cycles which you commonly see in your jet aircrafts and which is used for producing the power or producing the lift for your aerodynamics or aero engines. Okay, so now coming towards the basic principle behind it, okay, and how it's look like. So we will see that how the gas turbines work and where we have to use these type of gas turbine over daily life. Okay, so this is the introduction one. Okay, so this is how the gas turbines look like. I hope you already seen these type of gas turbine aeroplanes. Okay, so gas turbines have been used for electricity generation in the period of peak electricity demand. So if you remember that I already told you, whenever we have to produce some efficient power plant, usually we have to combine two systems, which is the steam power plants and the gas turbines. Okay, so usually gas turbines are not alone used for the electricity generation purpose for producing the daily electricity uses. So we have to use the steam power plant and turbines, gas turbines collectively. Okay, but in the aeroplanes we use the gas turbine only. Okay, we will see that what are the working principle also. So gas turbine can be started and stopped. Okay, so this is the advantage enabling them to brought into service as required to meet the energy demand peaks. Okay, and another advantage is that it is a small unit sizes and it has but the disadvantage is that it is low thermal efficiency if we are using gas turbines alone. Okay, but if we are using with the steam power plants, then it has the high thermal efficiency. So restricted the opportunity for the wider use of electricity generation. Okay, so this is the introduction of the gas turbines. So gas turbines are also called the combustion turbines, and it is a type of internal combustion engine. As you already know that internal combustion, where the combustion takes inside your engines. Okay, so, and we already discussed two other types of engines, which are the external combustion, which is Stirling and Ericsson cycle. Okay, so in this type of gas turbine, which burning of the air fuel mixture produces hot gases that spin a turbine to produce power. So important point is as comparison to the previous cycle, that is the diesel engines or auto engines or fuel engines, okay, where we have to produce some combustion process in order to generate some reciprocating motion. But here what we have to do is, as a result of combustion, there is exhaust gases will generated. Okay, and these exhaust gases are used to spin the turbine to produce the power. Okay, so in this case, we are not using the combustion process to produce some power, but here we are using the resulted gases, which is the exhaust gases, as a result of combustion. Okay, to spin the turbine, and that converts that produces some rotary motion, and then we can convert that rotary motion into some useful work. And it is the production of hot gases during fuel combustion, not the fuel itself, that give gas turbines the name. Another important point is that the combustion occurs continuously in the gas turbine in comparison to the reciprocating IC engine, in which combustion occurs for some time. Okay, so we already see that when there is a internal combustion engine, that is dual or any type of other auto or diesel cycle, for some time there will be combustion take place and then it will stop. Okay, and then we generate some sort of work. But here in the gas turbine, the combustion is the continuous process. That combustion cannot be stopped over the gas turbine. So we will see one video also, so that you will get some understanding that how the gas turbines work. So, this is how the gas turbines look like. Okay, so in this case, gas turbine, we have three major components. Okay, so this one is your compressor part. Okay, so the compressor part basically, the main purpose of this is to we have to intake some air. Okay, so this air can be intake from the atmosphere. Okay, so it will increase the pressure inside the compressor, and you already know that whenever there will be compression process, so its mean temperature will increase. So it's mean that we get some high temperature at this section. Okay, and this is your combustion chamber also. Okay, so there will be compressor. This is your combustion process. Combustion take place. Okay, and if you can notice over there are some small tubes that are placed around the combustion chamber. Okay, so these are basically the fuel injector. So here we have to continuously supply the fuel through these injectors, and then this is your turbine section. Okay, where we have to convert and the motion which is coming from your exhaust gases. Okay, so as a result of combustion, the exhaust gases move towards the turbine section, and inside this section, in the turbine section, there are some blades. Okay, so as a result of these exhaust gases, that blades rotate, and that will convert some, make some rotary motion, and then we will use that rotary motion into some useful work. Another important point is that you can notice here that your compressor section, your combustion section, and your turbine section are connected to same shaft. Okay, so this is an important point. Okay, so now we will see one video, and then we will discuss later about the working principle. Okay, so this is how your gas turbines look like. Okay, so this is your compressor section. This is your combustion section, and then there will be a turbine section. Okay, so if you can notice over there, your compressor section consists of several blades. Okay, so there will be two sets of blades. First set is the revolving one. Okay, so if you can, these are continuously revolving. Okay, and second set is the stationary. Okay, so the purpose of this is to just whenever the flow will pass through these blades, so it will increase the pressure. Okay, and these are called the compressor stages. Usually there were many stages inside your turbine. Okay, so we call it that as a low pressure stage, which is at the inlet section, and then as we move towards the combustion, there will be a high pressure stage. So these are the two set of plates, and then the air is flowing towards your combustion chamber. Okay, and as the air goes to these blades, the pressure increases. Okay, so these are the low pressure stages. These are the high pressure stages. Then this is the combustion process take place. So high pressure air is injected towards your combustion chamber. Okay, and this is your combustion process where the fuel is mixed with air. Okay, with the help of the fuel injectors. Okay, so these are the fuel injectors which I already told you that these are placed around your combustion unit. Okay, so this is the annular type of, and then this is the ignition plug also, similar to the motorcycle. Okay, and this is the conversion process take place, which is at the continuous level. Okay, it will not stop as we see in the auto and diesels. And this is the turbine section. Okay, so this consists also of several grades. Okay, so the exhaust gases which are resulted from the combustion process will move towards the turbine section and passes through these blades and result into the rotary motion of these turbine. Okay, another important thing is that I already told you that your turbine section, combustion chamber, and your compressor is connected to the same shaft. Okay, so whatever the power which we have produced at the turbine section, some of the power is utilized to run the compressor auxiliary equipment as well. Okay, and this fraction which is transferred back towards your compressor section, we can denote it as a back work ratio. Okay, so the fraction of the turbine work which is sent back to your compressor because it is connected to the same shaft. Okay, so this is how the gas turbines work. So I hope you will get some idea. So now coming towards the lecture again. Okay, so the thermal efficiency of the gas turbine is 20 to 30% compared with the modern steam power plants. Okay, so in future it is possible to construct the efficiency in and around 45%. So this is the target right now nowadays to achieve that gas turbine will produce up to 45% efficiency in comparison to the steam power plants. Then there are following fields where we have to apply these type of gas power plants: the power generation industry, the oil gas and gas industry, aviation, and marine propulsion. A gas turbine is used in the aviation and marine field because it is self-contained, lightweight, not require cooling water, and fit into the overall shape of the structure. Okay, so important point is that in comparison to the steam power plants, where we have to use water to cool the equipment, okay, but here in the gas turbine, it do not require cooling of through the water because air is passing towards to your gas turbines, and the same air which we have to use for the compression process is used for the cooling purpose also. Okay, so this is the advantage of the gas turbine, and it is selected for the power generation because it is simple, lack of cooling water, need quick installation and quick start. And it is used in oil and gas industry because of cheap supply of fuel and low installation cost. So some limitation also associated with the gas turbines. So they are not self-starting. So the starting of the gas turbine is very difficult, that as comparison to diesel or any other type of engines. It has low efficiency at part loads, non-reversibilities, and there are many reversibilities which are associated with the gas turbines. And another drawback is high rotor speed. Okay, so because if we already see that in the video also that there are some rotor blades are involved in it. Okay, and whenever these rotor blades rotate, okay, so these are rotating at very high speed. When there will be high speed, it means there will be high stresses involved in it. So it means we have to build over rotor blades some sort of very high strength alloys or composite material. So that will be very expensive. So low overall plant efficiency of the gas turbine. Okay, so these are some points related to gas turbines. So we already see that there are components, some of the components which make the gas turbines plant. This is turbine, compressor, okay, used to compress the air, then combustion chamber, and there are some auxiliary devices. So like there will be a starting device, there will be a lubricating pump, fuel pump, oil system, and duct system. Okay, so this is the schematic which is shown over there, which I already told you that air is intake towards your compressor will result in the high pressure gases over this part. Okay, then it will send to the combustion chamber where the combustion takes place, and due to the result of combustion, exhaust gases will pass through the turbine blades and it will result in the rotary motion of the turbine. So then, based on the classification, there are two types of gas turbine which are commonly used. One is the aeroderivative and one is the industrial type. Okay, so aeroderivative is shown over there. So this is the same turbines which we use in the jet aircrafts. Okay, so these are the aeroderivative. And then there are industrial type, which are big units of gas turbine, okay, which are used for the power generation purpose. Okay, so aeroderivative units are aircraft jet engine modified to drive electrical generator have a maximum output of 40 megawatt. Okay, so it has a not a very high output, okay, for the aeroderivative. Okay, so these can produce full power within 3 minutes of after startup, and they are not suitable for the base load operation. Okay, so as comparison to the industrial gas turbine, so it ranges size to more than 260 megawatt. Depending on the size, startup can take place from 10 to 40 minutes to produce the full output. Industrial gas turbines have low capital cost per kilowatt installed than aeroderivative units because of their more robust construction are suitable for the base load operation. So these are some classification of the gas turbine which we commonly see in our daily life. Okay, so then coming towards the advantages of the gas turbine over the steam power plants or the diesel engines. Okay, so the work developed per kg of air is more as comparison to diesel plant and also as comparison to steam power plants. Okay, so then there will be less vibration because there are no reciprocating motion. I already told you that these are not a reciprocating type of machinery, which is the gas turbines. These are basically the rotary machineries. Okay, so in the rotating parts, okay, so there will be a less vibration, okay, as comparison to the reciprocating parts. Then less space requirements, capital cost is less, and it has a high mechanical efficiency. So these are two terms, mechanical efficiency and thermal efficiency. Although it has a high mechanical efficiency, but it has the low thermal efficiency. So it is up to the design engineers. So what are their requirements? Either they have to produce a high mechanical efficient system, or either they have to build some high thermal efficiency equipment. Okay, so this is on the design engineer. Running speed of the turbine is large, and then low installation and maintenance cost of the gas turbines. Torque characteristics of the turbine plants are better than diesel plants. Ignition and lubrication system are simpler for the gas turbines. Then specific fuel consumption does not increase with the time in gas turbine plant as rapidly in the diesel plant. Okay, so this means that whatever the fuel we are using, so the fuel burn per unit time does not increase with time in the gas turbine plant, okay, as compared to the diesel plant or as also the steam power plants. Poor quality of fuel can be used. Lightweight with reference to weight to power ratio is less for the gas power plant, and smokeless combustion is achieved in the gas power plants. Okay, so these are some points, advantages. Then we will see also disadvantages associated with it. So disadvantages are the poor load efficiency. Then I already told you that we are working on the high speed of the rotation of the blade. So for that we need special metals and alloys to build that type of components. And then special cooling method required for cooling of turbine blades. It has a very short life because we are talking about very high speed of the flow. Okay, so it's mean that there will be a short life of your components. And thermal efficiency is low. wide operating speed, and the fuel control is difficult. Need to have a speed reduction devices for higher operating speed of the turbine, and it is difficult to start a gas turbine compared to diesel engine. Manufacturing of the blade is difficult and costly. Same output gas turbine produces the 5 times the exhaust gases than internal combustion engine. Okay, so these are some disadvantages as compared to the steam power plants and the diesel cycle. So if you have any question, you can ask, and then we move to the next. Okay, so working principle we already discussed in the video also, and I already told you that the main purpose of your gas turbine is that there will be an air compression process. So where we have to increase the pressure of the air, then it will take towards the combustion chamber where we have to mix fuel with the pressurized air, and then as a result of combustion process, the exhaust gases will generate, and that exhaust gases will send into the turbine section where we have to rotate the blades of the turbines. So these are the same working principle that I already discussed previously. Okay, so you just have to go through it by yourself. Combustion chamber is there, turbine section. Okay, so based on thermodynamics, we have to classify the gas turbine into two types of cycle. One is the open cycle gas turbine power plant, and one is the closed cycle gas turbine power plant. So in the open cycle, in this type of plant, the atmospheric air is charged into the combustion chamber through the compressor, and the exhaust of the turbine also discharged to the atmosphere. Okay, so open cycle of the gas turbine basically used in your jet engines. Okay, where we have to see that the air is intake from the atmosphere. Okay, then it is sent to the combustion chamber, and then it is sent to the turbine, and the exhaust gases, which are as a result of the combustion, will be released towards your turbine and then towards the atmosphere again. So this is the open cycle gas turbine power plant, so which is used in the jet power engines. Then there is a closed cycle gas turbine power plant also. Okay, so in this type of power plant, the mass of air is constant or another suitable gas used as a working fluid, and they circulate through the cycle over and over again. Okay, so these closed cycle gas turbine basically used in your power production processes where we have to generate some useful power to run some building or any other industry. Okay, so in that type of case, we have to use closed cycle gas turbine power plants. Okay, so open cycle gas turbine engines are the schematic shown over there. Okay, so I already told that we have to take air from the atmosphere in the open cycle, send it to the compressor, then it is compressed to high pressure at point number 2. Okay, and then the high pressure rise air is sent to the combustion chamber where it is mixed with the fuel, and then the combustion takes place in the combustion chamber, and then the exhaust gases will result at point number 3. Okay, and then it is sent to the turbine section where the expansion takes place, and then due to the result of the exhaust gases movement and the expansion process, we generate W net, which is the useful work, and then the rest of the gases are released again towards your atmosphere. Okay, so this is the working principle of your open cycle gas turbine, and these are used in the mostly in the jet aircraft. So now coming towards the closed cycle gas turbine. Okay, so these are the closed cycle gas turbines which we use in the power production industry. Okay, so where we have also the compressor, where we have to send some air or any working fluid so that the compression takes place. And at point number 2, we will get the pressurized air, and then we send it the heat exchanger where the combustion takes place. Okay, and then we send it to the turbine section where there will be expansion process, and then it is again sent to the heat rejector source where we have to reject some heat, and then the cycle will complete. Okay, so and the cycle which is associated with the gas turbines are called as a Brayton cycle. Okay, so this is the name of the cycle for thermodynamic analysis of the gas turbines. Okay, so in this type of Brayton cycle, we have 4 processes. So first process is the compression process, where that takes place isentropically in the compressor, and then there will be a constant pressure heat addition process, and then there will be isotropic expansion process in the turbine, and then there will be a constant pressure heat rejection process in your heat exchanger. So these are some processes. So now I will draw the TS and PV diagram so that you will get some understanding how to draw the PV and TV diagram of the Brayton cycle. So coming to the TS diagram first. Okay, so starting from the process 1 to 2. Okay, so for 1 to 2 it is a compression process and it takes place isentropically. So it means that entropy is constant and whatever the temperature is at T1, T2 will be higher as comparison to the T1 because the compression takes place and due to the compression the temperature increases. So for example, this is your first point and this is your second point and this takes place at the isentropy. Okay, then there will be a 2 to 3, which is a constant pressure heat reduction process. Okay, so it's mean that whatever the temperature at point number 2, the T3 will be higher as comparison to the T2 because the heat is added towards your and there will be a heat addition process. So it will be drawn like this that your point number 4 is somewhere point number 3 somewhere higher at as comparison to point number 2. So now 3 to 4 again it is a expansion process and it takes place isotropically. So and the temperature will drop, okay, and it will reaches towards the point number 4 and it is also isentropic process. So then there will be a heat rejection process from 4 to 1. Okay, so whatever the temperature at point number 4, so the point number 1 will be below point number 4. So this is the 4 processes. So this is your Q in, this is your Q out, and you also have to look at this is at constant pressure, and this is also at constant pressure, and this is your expansion process. 3 to 4 is your turbine, and this is your compression process. Okay, so this is the Brayton cycle, TS diagram. You have to note it down, then I will move to the PV diagram. If you have any question, you can also ask. So now PV diagram. So for PV diagram, so again from 1 to 2 it is a compression process. So it's mean whatever the volume at point number 1, the point number 2 is at the less volume as compared to point number 1. Okay, so for example, point number 1 is here. Okay, so I will just draw and this is your point number 2. Okay, they shifted towards the decreasing volume because the compression takes place. Then from 2 to 3, it's a constant pressure heat equation. So it's mean that until point number 3, it is a straight line because it is a constant pressure process. Then 3 to 4, it is the expansion process. So whatever the volume at point number 3, till it reaches towards the point number 4, the volume increases. Okay, so it means that it will shift it towards the right side of the PV diagram. Okay, so this is point number 4. Okay, then there will be from 4 to 1, again it is a constant pressure process. So you have to draw a straight line and just have to complete the cycle in this way. Okay, so now here we have Q in takes place constant pressure, Q out takes place also at the constant pressure, and then this S is equal to constant, entropy is constant, S is equal to constant, and this is your expansion process, and this is your compression process. Okay, so this is the PV diagram of your Brayton cycle. So you have to draw it, and we will move towards the development of the efficiency equation because our main target is to find the efficiency of the cycle which is associated with the gas turbines. Okay, so we will also try to grab on the relation for finding the efficiency. these are the clear PV and TS diagram. For your reference, you have to go through it by yourself. Okay, so you will get some idea of it. Okay, so the efficiency equation of your Brayton cycle looks like this for the air standard assumption. Okay, so 1 minus 1 over Rp, K minus 1 over K. Okay, so the Rp is basically the pressure ratio. Okay, so pressure ratio is the ratio for the maximum pressure over minimum pressure. So if you can correlate with the PV diagram, you can notice that your maximum pressure is at point number 2 and minimum pressure is at point number 1. So P2 over P1 is the pressure ratio. Okay, so in theory, the pressure ratio goes up, the efficiency rises. The limiting factor is frequently the turbine inlet temperature, and the turbine inlet temperature is restricted to about 1700 Kelvin, 2600 degree Fahrenheit. Okay, so these are some terms, okay, for efficiency. So we will see how we can drive this type of relation. So before this, we have another term which is we call as the back work ratio. Okay, so which I already told you when we are seeing the video, and that the back work ratio is defined as that the fraction of turbine work used to derive the compressor, and that is called the back work ratio. And for back work ratio, if in the question is mentioned, you have to find the back work ratio of your gas turbine. So simply you have to do is you have to just compressor work. Okay, so take the ratio of compressor work to turbine. Okay, so you will get the back work ratio of your turbine. Okay, so this is how we have to find the back work ratio. Okay, starting from the development of the equation, which is for the efficiency. So again, I will quickly draw the TS diagram first. Okay, so as you already know that whenever we have to develop the equation, we have to start with the energy balance equation. So for the process Q in, okay, so for Q in, which is from 2 to 3, okay, so and it's we can say that it will be equal to Cp T3 minus T2. Okay, so because it will be at the concentration, Cp T3 minus T2. Okay, so then there will be a Q out. So Q out is also at concentration 4 to 1. Okay, so we can also say that Cp T4 minus T1. Okay, so as you already know that your delta H change in efficiency is equal to Cp delta T. Okay, so we can also say that it will be equal to H3 minus H2, and we can also say it will be equal to H4 minus H2. So to develop the efficiency equation, we already know that 1 minus Q out over Q in. Okay, and simply we have to put the values that 1 minus Cp T4 minus T1 and Cp T3 minus T2. Okay, so Cp can be eliminated from denominator and also numerator. And from here we can also say that okay, so now this is the equation, efficiency equation, which we have to use for the reference. So what we have to do is simply we have to put the values of T3 and T2 in this equation, and we can derive these values for T3 and T2 from simple isentropic relations. Okay, so first relation which is valid for the isentropic process is T2 over T1. Okay, because 1 to 2 is the isentropic process, and we can say P2 over P1 K minus 1 over K. Okay, this relation we already seen in the start of the gas power cycle lecture. Okay, then another relation which is for isentropic process is T3 over T4 is equal to P3 over P4 K minus 1 over K. So these are the relations for the isentropic process. And I already told you that there is a pressure ratio involved in your Brayton cycle, and that pressure ratio we have to define as Rp, which which is equal to the maximum pressure. The maximum pressure is at point number 2 and minimum pressure is at point number 1, P2 or P1, and P2 is also equal to P3 and P1 is also equal to P4. Okay, so from here we get the pressure ratio. It is the ratio of maximum pressure over minimum pressure. Okay, so from here we can easily say that T2 is equal to T1 and P2 or P1 is the RP, which is the pressure ratio, K minus 1 over K, and for the similar thing we can apply for the second relation and we can say that it is equal to P3, T4, and P3 over P4 now becomes inverse of RP, okay, because we can write 1 over RP. P3 or P4 is RP, because we already see that it is the ratio of maximum pressure. So P3 is at maximum and P4 is minimum. Okay, so RP K minus 1 over K. Okay, so now we have the values of T2 and T3 with us. Okay, so simply we have to put the value of T2 and T3 in the efficiency equation. You can see it is equation number 1. Okay, so we will see that what resulting. Okay, so T4 minus T1 and T3 value is T4 RP K minus 1 over K and minus T2 value is T1 RP K minus 1 over K. Okay, so from here if we can just take common T4 minus T1, take common RP from the denominator, RP K minus 1 over K. So T4 minus T1 can be easily eliminated. Okay, so this can be cancelled if we just take RP common from the denominator. So it will be equal to 1 minus 1 over RP K minus 1 over K. Okay, so this is the equation for your efficiency which we already see. So if we have the value of RP with us, which is the ratio of maximum pressure to minimum pressure, and we have the value of the specific heat constant, which is the K, for the working fluid, so we can easily find thermal efficiency for the Brayton cycle. And this relation is only valid for the air standard assumption. And if we have to find for variable specific heat, then we have to use the enthalpy value, which is H3 minus H2, H4 minus H1, and simply we have to put in these relations so that we will get the value of enthalpy. So this is how we have to develop the equation for your Brayton cycle. So if you have any questions, you can ask me. So you have to note it down and then we will do the next one. Okay, so we will take 10 minutes break, okay, and then we will join again after 10 minutes. starting again from the example. Okay, so this example is example 9-5 from your book. Okay, so first you have to read the statement. A gas turbine power plant operating on ideal Brayton cycle. Okay, so it was mentioned over there that the gas turbine and the Brayton cycle is the cycle associated with it. At a pressure ratio of 8, okay, so maximum pressure, minimum pressure ratio is mentioned in the question. The gas temperature is 300 Kelvin at the compressor inlet. Okay, so compressor inlet is at point number 1. So if you correlate to the TS diagram. Okay, and then 1300 Kelvin at the turbine inlet. So turbine inlet is at point number 3. And it is also as a maximum temperature point. Okay, so utilizing the air standard assumption and variable specific heat, determine the gas temperature at the exit of the compressor and the turbine. Okay, so we are interested to find the value of the gas temperature, which is at the exit of the compressor. So exit of the compressor is at point number 2 and exit of your turbine is at point number 4. Okay, so back work ratio, we have to find the ratio of the work for the compressor to work for the turbine. Thermal of efficiency on the cycle. Okay, so this is the question, so you have to note down the data, then try to solve this. Okay, so first we will solve using the variable specific heat. Okay, because for the older standard assumption it's very easy. Okay, we simply use the relation which we already derived in the previous slide. Okay, because we have know the pressure ratio in the question. So just we need the pressure ratio and specific heat value for the, and we can easily find the value of thermal efficiency using the cold standard air assumption. Okay, so coming towards the part number A, using the variable specific heat. So T1 is known to us. Okay, so T1 is equal to 300 Kelvin from your question. Okay, so simply you have to go to table A17. Okay, so from table A17 you have to find the value of enthalpy, because in order to find the efficiency we need the enthalpy value at point number 1, at point number 2, at point number 3, point number 4. Okay, so first we will just note down the value of enthalpy. So you just have to go to A17 by yourself. So it will be 300.19 kilojoule per kg for T1 is equal to 300 Kelvin. Similarly, we also have to note another parameter, which is the relative pressure at point number 1, which is the dimensionless quantity. It will be equal to 1.386 for T1 is equal to 300 Kelvin. Okay, so now H1 value is known to us, so we have to move towards the point number 2. So for point number 2, we need another parameter, so we can find PR2 first. Okay, and then we will find using the PR2 as a reference point to thermodynamic table. Okay, so PR2 over PR1 you already know for the isotopic process. Is equal to P2 over P. So from here we can easily say that PR2, because PR1 is known to us, so 1.386 on thermodynamic table, and P2 over P1 is equal to it's the RP. Okay, so RP is known to us from the question, which is 8. So simply we can multiply the 8 turns out to be 11.09 PR2. So now we can use this point as a reference, PR2 value, in order to find the LPR point number 2. So simply you have to go to thermodynamic table and find out the value of H2 against it. Okay, so by using the first interpolation of table A17, it turns out to be 544.35 kilojoule per kg. Or similarly, we are interested in to find the exit temperature of the compressor. Okay, so you have to use the second interpolation for T2. Okay, and you have to just find by using the PR2 value as a reference 540 Kelvin. The T2 is now known to us from the thermodynamic table A17. Okay, now moving towards the point number 3. So T3 is known to us from the question, which is 1300 Kelvin. Simply you have to go to thermodynamic table. You can easily find the value of H3 against 1300 Kelvin without interpolation. So you can just note down the value 1395.97 kilojoule per kg. And you can also use another parameter which is PR3 against the same T3, which is 330.9. So now apply another equation for the isentropic process 3 to 4, which is PR4 is equal to P4 over P3 into PR3. So PR3 is now known to us from this part, and P4 over P3 is basically the inverse of pressure ratio. Okay, so simply we can say 1 over 8, and PR3 is 330.9. If we can solve it, it turns out to be 41.36. And by using this reference now, we simply go to thermodynamic table again and have to apply the interpolation. For the first interpolation, we can easily find the value of H4, but we need all the enthalpy values. So it will be 789.37 kilojoule per kg. And now for part A, we have to find the T4. So T4, you have to apply for another interpolation. You can simply find out that it will be 770 Kelvin for your T4 by using the interpolation. So this is our question for part A, solution for part A, where we have to find the compressor exit temperature and turbine exit temperature. So the part A is done, so you have to note it down, then we'll go to the next one. So in the part number B, you have to find the backward ratio. So backward ratio is basically the ratio for your compressor work over turbine work. So the compressor we have to supply the work, and turbine we will get some work. Okay, so for compressor, the compressor is between 2 to 1 and turbine is between 3 to 4. Okay, so we can simply say that your compressor work is equal to H2 minus H1, okay, because we are using the variable specific equation, so that's what we have to use, and that is value. Okay, and then if we can use the value from the part A, so H2 value is 544.35 and H1 value is 300.19. Okay, so simply you can solve, you will get the value of WC, which is 244.16 kilojoules per day. And similarly, you have to find the turbine out. So for turbine out, we can simply use H3 minus H4. Okay, and for H3 minus H4, we will have the value which is 1395.97 minus 789.37. Okay, and you can simply find out that it will go to 606.6 kilojoule per kg. Okay, so you can simply put the value in the back work ratio equation, which is WC divided by WT. So it will be 244.16 over 606.6. It comes out to be 0.403, or you can say 40.3% of the back calculation. So it means that 40.3% of the turbine work output is used just to drive the compressor. Okay, so this is the meaning of your back calculation. So in this case, we are using the variable specific heat assumption. However, you can use also the constant specific heat, which is the gold standard heat assumption. Simply, you can use for back rotation. If I can say it will be, you have to find for gold standard heat assumption. So you already noticed that it will be H2 minus H1 over H3 minus H4. Okay, and from here we can easily say that it will be equal to Cp T2 minus T1 over Cp T3 minus T4. Okay, so Cp will be eliminated, so we can use the value of temperatures we have with us, T2 value, T1, T3, T4, and simply put it into this equation. You will get the back relation using the gold standard heat assumption or using the constant specific heat calculus. Okay, so you have to note it down and go to the next one.
एक्सक्यूज मी सर
जी
सर ये बैकवर्ड रेशियो में क्या शो होती है ये थोड़ा
अच्छा So basically, back ratio, I have already told you that when you are seeing the turbine, gas turbine working, okay, so your turbine section is connected to the same shaft with the compressor shaft. Okay, so it means that your shaft is common for the compressor part and your turbine part. Okay, so it means that whatever your work is producing from your turbine section, some of that work is transferred towards your compressor part as well. Okay, so the meaning of your back rotation is that the fraction of turbine work used to derive the compressor, that is called the back rotation. Okay, so it is some fraction that is used to run the turbine, run the compressor. Okay,
तो सर और सर इसमें मेरे को पार्ट ए में जो पी आर फाइंड किया वो पी आर क्या चीज़ है
क्या चीज फाइनल की है
पी आर फाइंड आउट किया पी आर 1 पी आर 2
अच्छा मैं आपको बताऊँ Okay, so if you can notice from the previous lecture, whenever we have to assume that there is a variable specific heat problem, okay, so you have to go to thermodynamic table, and in thermodynamic table for the working fluid as a air, so you have to go to a table A17, okay, where we have to find the relative pressure values, okay, and you can also find any other parameter if you have the data available. So simply it is the relative pressure. Okay, and similar, there is relative volume also available in your table A17. Okay, so this we already practiced in the previous lecture. Okay, so this is not a new thing. so this is your table A17. Okay, so in this case, there will be ideal gas property of air. Okay, so this is the table we are talking about. So this is the PR values, relative pressure values. And this is the relative volume values. Okay, so you can find any property. Okay, so the main target is to find enthalpy value and temperature value. So you can use either relative pressure or you can either use the relative volume also. Okay, so this is a dimensionless one. Okay, so this we already discussed in the previous slide.
Okay, sir. Okay, sir.
Okay, so coming towards the part number C. Okay, so in the part number C, our main target is to find the efficiency. So efficiency is equal to 1 minus Q out over Q in. Okay, so we already know that Q out is in between 3 to 2. Okay, so simply we can say that it will be okay, so Q out is between 4 to 1 and Q in is between 3 to 2. So H4 minus H1 over H3 minus H2. So now we have all the values of enthalpy. H4 is known to us from part A. H1 is also known to us. H3 is also known to us. H2 is also known to us. We can simply put the values in this equation and we will get the efficiency for the Brayton cycle. Okay, so this is the 789.37 H4 value. H1 value is 300.19. H3 value is 139.5.97 and H2 value is 544.3. So simply you can solve it and you will get the efficiency as 44.8%. Okay, thermal efficiency for the Brayton cycle. Okay, so if you have to use another relation we already developed, which is equal to 1 minus 1 over Rp, K minus 1 over K. Okay, so you can also use because Rp value is known to us. Okay, but this equation is only valid for the core standard air assumption. Okay, so because in this question, I mentioned that you have to compare, you have to use both assumptions, that is core standard air assumption and variable specific heat. So you can use for comparison Rp value for the this one. Sorry, this is I think mark it wrong. It will be equal to 42.6%, and by using the core standard air assumption, it will be equal to 44.8%. Okay, so this value is more closer towards your actual value, because for variable specific heat assumption, it will result in the closer value against your actual thermal cycle. Okay, as comparison to the core standard air assumption. So if you have any question, you can ask, and then we'll go to the next question. This is another question, so which is again from the simple ideal Brayton cycle, and this is question number 977 from your book. So first you have to read the statement. Stationary gas power plant operate on a simple ideal Brayton cycle with air as a working fluid. So air entered the compressor at 95 kilopascal and 290 Kelvin. So it's mean that T1 and T1 is known to you, and the turbine at 760 kilopascal and 1100 Kelvin. So it's mean that your and the turbine at, okay, so it means it is the entry point of your turbine. Okay, so which is the T3. Okay, it is the maximum temperature and maximum pressure. Heat is transferred to air at the rate of 3500 kilojoule, 35,000 kilojoule. So determine the power delivered by this plant. So in the part A, you have to assume constant specific heat at room temperature using the cold standard assumption, and part B by using the variation of specific heat at temperature. Okay, so this is the question. Okay, so for this question, you can easily find the pressure ratio from the data because RP is equal to P maximum or P minimum. Okay, so P maximum is 760 kilopascal and P1 is 95 kilopascal. Okay, so you just have to divide this two things and you will get the pressure ratio. So you have to note down the data, then you move toward the solution. So I will quickly draw the DS diagram first. So in the part number A, we have to use the air standard assumption. So we do not have to go to thermodynamic table. We just use the temperature values at all the points. Okay, so first we need to find the value of T2 because T1 is known to us. T1 value is 290 Kelvin and T3 value is 1100 Kelvin on the question. Okay, so we have to find the value of T2 and T4. Okay, so T2 over T1 is equal to P2 over P1 K minus 1 over K. Okay, so from here we can say T2 is equal to 290 Kelvin, P2 over P1 8 0.4 over 1.4. Okay, and it will be equal to 525.3 Kelvin for the value of T2. Okay, similar thing for the T4. So T4 we can also apply another isotropic relation which is valid for the 3 to 4 process. So T4 over T3 is equal to T4 over T3 K minus 1 over K. Okay, so P4 over P3 is basically inverse of your pressure ratio because we already discussed in the previous also 1 over 8 K minus 1 0.4 over 1.4 and T3 value is 1100 Kelvin from your question. So simply you have to solve it and you will get the value of T4 easily. So it will be 607.2 Kelvin for your value of T4. Okay, so now all the temperature values are known to us. Okay, so simply we can use the efficiency equation which is 1 minus Q out over Q in. Okay, and from here we can say that 1 minus T4 minus T1 over T3 minus T2. Which we already seen in the previous slides. Simply you have to put all the temperature values. So 1 minus 607.2, 290, T3 value is 1100 and 525, and this will be equal to coarse resolutions. Okay, so now the main objective of the part A is to find the power delivery. Okay, so for power delivery, we can say your W dot net, which is the power, is equal to efficiency into QE. Okay, so efficiency is known to us 0.448, and your QE value is known to you from the question. Okay, so which is 35,000 kilojoule, which is mentioned in your question. Okay, so simply you have to multiply these two factors and you will get the W net. Okay, so W net is equal to 15680 kilojoule. This is how you have to find the power delivery. This is the solution for your part number A. Okay, if you have any question, you can ask, and then we move to the part B. So in the part number B, we have to use the variable specific heat assumption. Okay, so for variable speed heat assumption, simply we use the T1 value, so which is 290 Kelvin, and go to table A17. Okay, so from A17, you have to note down the value of enthalpy, because we need the enthalpy's value in order to find the efficiency. So H1 is 290.16 kilojoule per kg for you. Point number 1, and similarly you have to use the relative pressure at point number 1, which is equal to 1.23 double one, which is the dimensionless quantity. And similarly you need another parameter at point number 2, so that you will find the H2 value also. So PR2 over PR1 is equal to P2 over P1. So that turns out to be PR2 value is equal to 1.23 double one into the pressure ratio, which is 8. Okay, so simply you can multiply these two terms and it will be 9.8488. Okay, so using this PR2 value, simply you have to go to thermodynamic table A17, and by using the interpolation, you have to find the H2 value against this value, and you will find it will be 526.12 kilojoule per kg. Okay, so now coming towards the T3. So T3 is equal to 1100 Kelvin from your problem statement. Okay, so simply you have to go to thermodynamic table and find the H3 value, which is 1161.07 kilojoule per kg. So simply also you have to find another parameter, which is relative pressure at point number 3, which is equal to 167.1 dimensionless quantity. Okay, so now we can apply another isentropic relation for point 3 to 4, okay, so that we can easily find enthalpy at point number 4. So PR4 is equal to P4 over P3 PR, so which is equal to 1 over 8, which is inverse of your pressure ratio, and 167. This turns out to be 20.8 PR. And from here we can easily go to thermodynamic table, and by using this point PR4, we can apply an interpolation and we can find the value of H4, which is equal to 650.9 51.37 kilojoule per kg. Okay, so we have all the enthalpies value with us. Okay, so H1 is known to us, H2 is known to us, H3 is known to us, and H4 is known to us. Okay, so we can simply use these values to find the thermal efficiency. Okay, the thermal efficiency is equal to 1 minus H4 minus H1 or H3 minus H2. Okay, so by simply putting all the values H4 minus H1 H2 minus H2, okay, so you will get the value 0.431, okay, for the thermal efficiency. Okay, so we are interested in to find again the power delivered. Okay, so power delivered is W net is equal to efficiency, which is 0.43, and Qin, so Qin is 35,000. Okay, so which is mentioned in your question. So simply you have to multiply these two, and you will get 15085 kilowatt of power delivered. Okay, this is the solution for your particle B by using the variable specific heat. So if you have any questions, you can ask me or you can do it answer. So here is the question which you have to solve. Okay, so the question is same, which we already solved in the previous slide. So only the data is different. So here it is 45,000, and some of the temperature is different over there. Okay, so you have to use constant specific heat assumption and variable specific heat assumption to find the power delivered. Okay, so again you will get 0.2 epsilon now for all the students. You will send it to me in the clear way. Okay, and I will again remind you all. Okay, so that tomorrow there will be one quiz, okay, which is related to dual cycle. Okay, so and it will be 15-minute quiz. Okay, so be prepared for the quiz tomorrow by using the previous lecture, which is the dual cycle. So if you have any question, you can ask me, and then we will just stop over here.
सर ये डायग्राम बनानी होगी पीवीटीएस डायग्राम कल के
जी
क्वेश्चन में।
बिल्कुल क्विज में भी और हर आपके पास सभी जब आपका फाइनल होंगे तो पीवी एंड टीएस डायग्राम इज वन ऑफ द मोस्ट इंपॉर्टेंट पॉइंट स्टार्टिंग पॉइंट while solving all the problems related to thermodynamics. So make sure you all have to practice it, that to draw the correct PV and TS diagram, because I have noticed that most of the students which send it to me in the assignment question draw PV and TS diagram wrong. Sometimes the constant pressure process is there and they will just represent with the constant volume process. So you have to practice it by yourself. Okay, so important point is that TS and PV diagram is most important point while solving the problems. Okay, and it have some sort of marking distribution also in all the questions. Okay.
Okay, sir. Thank you.